All right. So since we're not meeting on Wednesday, I do have some stuff. Some stuffs for you.
How about homework?
I do.
One of those?
I do have one of those for you.
Cool.
It's too
You're not complaining, are you?
No, never.
Okay. All right.
When would I ever?
I've never heard you complain.
Yeah.
That's why I was like, what's going on here? So from here, just do three. Do any three.
5.2.3.
Just pick the ones you want. They're
Oh, okay.
systems. They're just
Okay.
systems to like find the just to classify.
Okay.
Classify the fixed points. So there's like A through fucking whatever,
Okay.
and pick any of those three. And then this one we'll probably want to talk about. And since we're not meeting on Wednesday, I might do a little video.
Is that a 5.7 or a 5.2?
That is a 2.
Okay, I was a little concerned.
Yes.
A little concerned.
I appreciate
We're
it. I
skipping ahead,
acknowledge your
people.
concern and I appreciate it.
5-7, here we go.
And then these
We're in there.
And then these are just fun. These are all relationship systems. So they're really pretty awesome. We're gonna do that today. We gotta get to it. We've got to get to it.
Are you ready to talk about this on Monday?
Yeah.
Okay.
That's cool.
Yeah. Let's chat. So how about a week from tomorrow or Wednesday? Like next.
Do next Wednesday.
Do next Wednesday.
Okay.
Got it.
Yeah.
Gotcha.
I don't think you're gonna have a lot of trouble with this. It's too cold for that. It's also too hot for this. Well,
There's no
Weird
balance.
time
it's
in
a
the
weird
middle,
time. It's a weird
It's not ever
time.
Wednesday.
So let's see. Where were we? I also forgot my notes. I left those at home, but I know what we're gonna do. I'm so excited about it all.
Is this the right notebook? It is.
Of course, this is what all your problems are about, and we were analyzing the system. And so to get a phase portrait, let's just refresh our memory, a phase portrait. And we didn't talk about all the cases, but they all have the same basic idea. One is we find the eigenvalues and eigendirections and corresponding eigendirections. Since this is a 2x2 system, we'll have 2 eigenvalues. We'll get a lambda that corresponds to V1 and a lambda 2 that corresponds to V2. And most of the time those will be different things, but not always. These might be the same, and we'll talk about what that means. But in general, probably the most things that could happen, or the most likely situation is this, and they're different. 2, so we find those eigenvalues. Do you remember how to do that? Let's refresh how to do that. So
Characteristic polynomial.
yeah. So solve lambda squared minus tau lambda plus delta equals 0. And here, tau is the trace of the matrix and delta is the determinant.
The trace is the
Sum of the diagonal going down. Yeah.
and then the determinant is AD minus BC.
Indeed it is.
Okay.
Indeed. So basically you get your matrix, figure out what it is, find these, create this, solve this. One thing you will notice that we're going to use today actually is that the eigenvalues are tau plus or minus via the quadratic formula. And that's actually, a lot of times writing something like that wouldn't be super helpful, but it's actually going to provide us with like a really cool little map of the way things can go in this world. This world here.
This one.
This one, not this one. This one has no map. 2, and then B, find corresponding vectors, and that would be by taking, so you do that, for each lambda, so twice, you're going to solve A minus lambda B, C, D minus lambda. So subtract the eigenvalue from the diagonal. Set a B1, B2 here, and a 0 on that side. And what you'll get from this is infinitely many solutions. And those infinitely many solutions describe a line. Sometimes they describe the whole plane, but things are pretty degenerated when that's happening. Like basically your matrix is just 0, and then everything's an eigen something. So solve that, and then sketch the. So this right here, I'm actually going to put this. This is if lambda is real. Lambdas are real. This is what you do. You're going to sketch the I vectors / directions, and these are going to be straight line trajectories. These equal our straight line trajectories. Oh, I'm so glad I get to start the day with you all doing this. This is like one of my favorite things.
Not only the day.
This is
but the
almost why I taught this course, just to have to talk about what we're talking about now. It's so beautiful. Yes?
So A and B are for 1 or for 2? Is that step 2?
This is step 1 still.
Yeah,
This is all still step 1,
Oh,
Kayla.
so 3 is C. I got
Yes.
you, I got you, I got you.
Gotcha,
Okay,
yes.
Sorry,
Thank you. Oh,
I'm
thanks.
on it.
Oh, all
You said
sorts
I
of
get it.
tricks.
AB3.
Yeah,
AB3.
I just
Thank
want
you.
to make sure I'm on the
Thank
same
you.
page.
I appreciate you putting me on the right page too. These are the straight line trajectories. And so let's just do a little example. Let's say I had V equaled 2, 1. Then over here I would sketch the 2, 1 vector. But then I would just make that a whole line. And in these systems, for the most part, the origin is going to be our main fixed point. And so if lambda was a negative number that corresponded to this eigenvector, then I have contraction toward the origin. So this would be like lambda negative. If lambda were positive, let's say V equal negative 2, 1. So I had something like this. 1, 2, 1. And that yield eigendirection like that. And I had lambda positive, then we have expansion. So instability. So stability, instability. Does that make sense? Stable,
Yeah.
unstable. With a positive eigenvalue. So it's, yeah. You can think of this as your velocity with respect to 0. And then, if we wanted to, we could go through and solve all this. Could write a general solution. And the general solution would look like this. xy of t is equal to some constant e to the lambda 1t times the corresponding, put lambda sub 1 here, corresponding eigenvector plus c2 e to the lambda 2t, corresponding eigenvector. And this would be if lambda 1 is not equal to lambda 2. If they're equal, then we got something a little funkier put in there, but it don't matter for this purpose. Kayla, may I help with anything?
On the straight line trajectory on the right, are you saying that when lambda is less than 0, then V is 2, 1, and then when lambda is greater than 0?
Yeah, and this is just an example. This isn't necessary. This vector could be anything, but I'm saying,
Oh,
just for example, if we had an eigenvector 2, 1, because I wanted to sketch something real,
so the 2, 1 corresponds to the left.
the left, and then the negative 2, 1. As you can see here, so negative 2, 1 for that
Okay.
guy, and then
Okay.
2, 1 for that one. Does that make sense?
Thank you.
Cool. If we get repeated eigenvalues, then things get weird because it's really challenging to actually find 2 different eigenvectors. You can do it. We're not going to mess with that a whole lot. What I'd rather get to is just kind of what happens there intuitively, and then we can worry about the details if we come across them. Any questions on this stuff? Seems
Good? Cool, cool. So let's look at this right here. This tells us the nature of our eigenvalues. And what's most important is what's under the radical. So if this thing, tau squared minus 4 delta, is a positive number, in other words, this thing under here is positive, then we're going to have tau plus a positive, tau minus a positive. So let me kind of write this up over here. So if tau squared minus 4 delta is positive, we have two different eigenvalues. Does that make sense why that would be? Because of this is a little positive thing here, and you're plussing and minusing it. So it's going to produce two different things. We don't know what the signs are. The signs will be determined by tau itself. We'll worry about that in a minute. If tau squared equals 4 delta, in other words, this thing underneath here is 0, what is that case? What does that mean when you just got this in the quadratic formula? When you don't have a plus minus, it's because it's 0. What is that?
Is that like a root bound?
Oh, just think algebra. Yes, it is. It is. It's a repeated root. Yeah, beautiful. Yeah. So that's a repeated root. When you have, so that would be something like this. If I had lambda squared minus 2 lambda plus 1 equals 0, and then I did the quadratic formula here, we would get 2 plus or minus square root of b squared. Okay, I got scared for a second. Minus 4 over 4 over 2, and so that's just 1 once, but that's because 1 is a repeated root. So when this thing equals 0, you've got a repeated eigenvalue. And then what is this? What happens when this goes on? When this is called the discriminant in general. When this thing, the discriminant is negative, what do I get? What happens then? Just looking at the quadratic formula, if tau squared minus 4 delta is a negative number.
It's not real.
Complex, right? Now we got imaginary shit in there.
Sure do.
Sure do. Yeah. So in this case, we get complex eigenvalues in vectors. And things can be pretty interesting then. Let's take a look at that really quick before we get into the math. Suppose I had lambda equals 1 plus or minus I. How about we just, let's do that. What the hell? And then I had these two corresponding eigenvectors, V and V conjugate are my eigen. Let's put a conjugate sign above that, because the eigenvectors will turn out to be conjugate. Notice how these are conjugates, right? One's a plus, one's a minus. Over here, you'll see that same relationship. These will be conjugates of each other, corresponding to the conjugates of these. But they will be complex matrices, so don't think they're going to be anything simple. It's kind of, we'll maybe come across some of those, and we'll worry about it when we do. But if I've got complex eigenvalues and complex eigenvectors, let's look at that general solution form. Then my general solution is going to look something like this. I'm going to have x of t, y of t equals c1 e to a complex number. So here I'm going to put 1 plus I t, and then I'm going to have complex vector v. Here, we'll call these, v and then v hat conjugate or something weird. I don't know, make up your own notation. They're two different eigenvectors. It don't matter really. That's not where the interesting part of what I'm going to say comes in. And then the other one's 1 minus I t, and then v hat bar. So let's do a little bit of work here. Notice that each of these has an e to the t in them, and an e to the it. This one's negative it.
looks legit. And then I can pull this e to the t out in front. How do I find e to the it?
Oops, what?
How do I reconcile that? What's e to the it? Someone had complex.
It was not.
What, do you remember what that is?
Is it side T?
It's close. It's close. There's some trick shit going on in there. This is Euler's identity, or Euler's formula.
We're doing complex stuff in electronics right now.
Oh, cool. Oh, nice, nice. That's where I'd expect it to be. That's cool. Does this ring bells? Right, you've seen this before.
I never took complex, so this is
But your Calc 2,
It's been
did you have Calc 2 with me?
no.
Okay, good.
It's
'Cause I was
been a
gonna say-
while, but I think I know.
Because I was gonna say, I got it, I had to
I
have shown this
should
because it's like one of the greatest things to ever see. You can prove this using Taylor series.
Oh.
So you look up the Taylor series of E, replace it with an I, then you group things and you'll see the Taylor series for cos plus I times the Taylor series for sine come out. So this is Euler's formula.
Euler's got all kinds of fun things in there.
Yeah, Euler was cranking out shit the minute he was born.
Yeah, apparently.
Yeah, pretty crazy. So I guess we'll accept that, but I do have to show you because you need to know this. That would mean that if let t be pi, you get e to the I pi equals cosine of pi plus I sine of pi. I'm glad we had this discussion because you can't graduate without having seen this. That'd be a crime. What's cosine of pi?
Right.
Sine of pi and
-1, what's sine of pi?
Zero.
Yeah, definitely. So e to the I pi plus 1 equals 0. That's Euler's identity.
That.
And that's pretty crazy.
Yeah, I think I've seen
That
that,
was familiar.
identity, but I don't
Okay.
know that I got to see how we got there.
Okay, cool,
Yeah.
good. Yeah, I'll happily show you anytime. Oh, we are having like a e minus 1/10 day in the math office from 3 to 5 today. So if you're around, you want to stop by, get some food. I made up a bunch of problems around E that we can use as opposed to socializing.
What's wrong with socializing?
I don't know, it's math people, they don't like to
Today is-
socialize. It's like
Today is e to the minus
Yeah.
1/10 day.
1/10 day, because E's 2.7.
I didn't know that. That's so special.
And I didn't want to come in on Tuesday. So we had E minus 1/10 day instead of E day.
I love that. He said best I can do. Take it or leave it.
Exactly, it's like approximately E day. It's good enough.
I love
Approximately
Good enough.
day.
See, everybody knows about Pi Day, but everyone forgets about
Well, that's the
P-Day.
thing. Part of my shtick is I hate Pi Day. I like to pretend like I really hate it.
That's a crime.
What
Yeah,
about
Pi's
Tau
just not
Day?
that great.
That's a crime.
E's better.
Have you seen the video about how tau is better than pi, and that someone made this argument that math should be centered around tau?
No.
Yeah.
What's tau?
2 pi.
What?
What?
Yeah.
I've never heard that. Oh wait, I have seen that video.
Yeah, okay.
I think I have seen
I
that.
swear to God,
Yeah, I was
hope
like,
it
yeah.
wasn't a
I
dream.
was like, wait, that runs some
I hope
bells.
it wasn't.
That would have been a weird dream.
Yeah,
It
yeah.
was funny.
But
It would be. But anyway, these are like the five most important constants
Okay.
linked together into one beautiful equation.
They're all
So,
really bad.
and I will show you this. I gotta show you this since you probably. This is actually one of the things on the little sheet, but I'll cheese out and. Oh shit! I wonder if I gave folks the right Yeah, I don't think I have the right info on that sheet, but what is e to the pi over 2I? What would that be? I need to fix that problem. God damn it.
So what?
Oh, we could do it. We could. Well, it's the square root of each side of this, right?
Apparently, it's
So I.
then
Yeah. Or you could
not. Or I can plug it in.
plug pi over 2 into the formula at the top. So e to the I pi over 2 is cosine of pi over 2, which is 0. Sine of pi over 2 is 1.
Okay.
So we get 1i. Now raise each side to the ith power. This is my favorite thing to do out of anything, because you get to write that.
I to the I.
And what is it equal to? What's I to the I equal to?
E to the pi half. Pi over 2, sorry, hello.
Close.
Okay.
What do you do with the?
Okay. She just accepted it. She said, okay.
Okay. It's close. It's e to, but what does the I times I give me?
-1.
-1, so negative
So
pi
I
over
can't
2.
just pretend. Okay, you're right.
Yes.
I think you were, Kaylee, you were right enough. I would have accepted it.
Yeah, it was pretty damn good.
Okay.
Yeah. I raised to I is a real number.
But it's an imaginary number.
Yeah, it was poorly named, as Trinity will tell you, because it like makes like electronic study possible.
Yeah.
Basically.
If you didn't have imaginary numbers, electronics doesn't make sense.
It wouldn't. Yeah, you couldn't do shit.
So who named it?
I don't know. People were scared of numbers. Like, you know, you like
Me too.
figure out 0 and then you're burned at the stake. You know, negative numbers make you burned at the stake. And people eventually were like, "Oh, it's fake.
0?
Don't worry."
Is
Yeah.
fake?
No, 0's not
No.
fake, but
They
But
thought
people
it
thought
was.
that it was?
They didn't think it existed, and then when it was discovered that it existed, it caused a lot of problems.
Just the concept of discovery.
it's like blasphemy because, like, why would
How dare
God leave a
you.
vacuum?
Yeah.
It's like, it's not a vacuum, dude. It's a fucking idea. Calm down.
Yeah.
My favorite is always go back to the pizza, okay? What happens when you eat the whole pizza? Do you have pizza left or is it gone? This is 0. No pizza equals 0.
Equals
None.
Equals
Zilch. Nada.
Oh my goodness. Okay, all right, back to this. So we gotta get to the relationships today.
I'm sorry.
You're not doing anything wrong. You're all good. But I can take that thing down there and replace the e to the ITs with cosines and sines.
I hate those.
We don't hate any math anymore. No. So letting
Attempts to.
e to the it equal cosine of t plus I sine of t, and then e to the negative it is cosine of t minus I sine of t. You just replace the t with a minus sign as an odd function. The minus comes out front. All good. You can work this all through to get x of t and some algebra.
And so,
Algebra.
don't forget about that.
Yeah, it's gonna be C1, so we'll have this e to the t that's just writing out front, but in here, we're just gonna have C1 cos t plus C2 sine of t. Hold on. Times a vector, this one's times a vector, times some new vector, we'll call it W, plus C2 sine of another vector, we'll call it W hat.
The hat.
Okay, cosine to Jesus.
This should be a t in here. So we just got these sine and cosine functions. We've got that e to the t out front. Cosine and sine mean spinning, right? They create rotation. This e to the t creates a magnitude change. So this e to the t is growth. These are rotation. And I've skipped a lot of details here, but we could get to this. And in fact, actually one of the problems I gave you kind of has you do something roughly along these lines. So that's rotation. So what we would see is something like this. Now I don't know the exact direction of rotation, but as we spin and grow, we get spiraling outward. So the rotation creates the vortex. The e to the t out in front creates growth outward. So here's the lesson. Complex eigenvalues mean spinning. And if we have an eigenvalue, so if lambda is a pure imaginary, you don't have a real part, then so if I hadn't had that 1, if I just had lambda was plus or minus I, that e to the t wouldn't have come out in front, and I would just have this, and it wouldn't grow or die, it would just spin. So if I have pure imaginaries, I get what are called centers. And this is just closed orbits.
It's like a circle.
Like a circle, absolutely. And they might have weirder shapes, right? It might be a little bit elliptical or something like that, but circles work just great. We get centers. If lambda equals a negative plus or minus bi, we have stable spirals because I've got this negative out in front. If that had been -1 instead of 1 as the real part, I would have e to the negative t out in front. And that would mean I was dying in magnitude as I went forward in time. So these are stable spirals. If lambda is a positive, as we've just seen, plus or minus some beta I have an unstable spiral. And all I really kind of wanted was you to get to believe that this is like a reasonable thing to expect. And it all comes about because of Euler's formula and the cosines and sines kicking in when you've got imaginary powers of E.
Imagination.
Imagination. Where's that from?
SpongeBob.
SpongeBob. Oh, I don't think I've never watched SpongeBob.
Well, that's a crime.
Really?
No, I'm sorry.
That's a crime.
I feel like I should.
The old SpongeBob in particular.
Yeah.
My brother has all of the seasons on DVD.
I'll have to check it out. I loved Ren and Stimpy. Did anybody watch that? Is that too
no.
old?
You might have aged yourself just a little bit.
I think you probably have a sense I'm older than you.
Maybe.
I mean, I'm aware.
Yeah, we're aware. Okay, so let's take this here with our slightly deeper understanding of what these complex eigenvalues do, and let's make a plane of possibilities. So here's delta, here's tau. So remember again that our eigenvalues are completely determined by these two things. And the formula was negative tau plus or minus square root of tau squared minus 4 delta over 2 for our eigenvalues. So notice how there's a boundary between these two cases, right? So we have, with tau squared equals 4 delta, we get repeated eigenvalues, but if it's negative, we've got complex ones with spinning. If it's positive, we have different eigenvalues. So, if we sketched out tau squared equals 4 delta in this plane, that's a parabola that opens sideways. It's this one. Delta is a quarter tau squared. So think of this as y and this is x. Your x-axis is vertical, kind of. Yeah, does that make sense? And then I've got this parabola like this. So this is tau squared equals 4 delta. Did you do this stuff, Trinity? Have you done this stuff before? Just saying.
Maybe not in this way.
Not this, yeah?
Yeah, I don't actually think I've ever thought about it.
Cool.
I'm gonna tell them.
All right, yay.
I promise you're teaching me something new. It's okay.
Okay.
I love that.
I was talking to Dr. Narcissi the other day, and I said, we were talking about you working on your thesis. I said, well, I think she's pretty, I think her classes are pretty trivial for her for the most part otherwise. She said, well, I hope not.
He said, well, you like were building airplanes in high school, so
Yeah, it wasn't that
did a lot of
serious.
experience. What's that?
It wasn't that serious.
Well, okay.
We just learned how to fly.
I was just talking.
Okay.
I only learned how to fly it. Don't worry.
You didn't build it.
It was just shitty simulations. It's fine.
Okay. It's when you build your own and get in it and fly it, that's when shit gets real, right? Like, oh my God, terrifying.
I did consider not going to college though and doing flight school.
Oh, wow.
Oh, that's
to be
fair.
honest.
That would have been a
That's
cool
fair.
life.
Yeah.
Oh.
I would have respected that decision fully.
Okay. So,
I thought about it more and more every day.
which region is this? So look, I've got like, so here's this parabola and it breaks the plane into two separate areas essentially, right? There's this to the right and there's all this out here. Which one is this?
T squared equals 4.
Yeah. Where is t squared minus 4 delta positive? Or where is t squared greater than 4 delta in that chart? Tau squared, called
Oh.
t. So what's delta on the tau axis? What's the value of delta here?
0.
0. So delta's 0 there. So notice that tau squared would be positive
Yes.
on this side of it then. So that means that this region out here is where we have tau squared greater than 4 delta. Or tau squared minus 4 delta is positive, and same down here. And that means we have two different eigenvalues.
Oh, that makes sense. Okay.
Yeah. So in this region, we have two different eigenvalues, and that looks like this. So let's draw a little chart for that. That means I've got some eigendirection like this, some other eigendirection like this. Got two different eigenvectors. One is going out at a certain rate, and the other is going out at a slightly different rate, or maybe they're both going in. The key thing is they're not going in opposite directions yet. We don't have that yet. Why is that? So let's put this back up. Let's check this out here. In this region, right here, so like this little region, why is this thing a positive number that is less than tau in magnitude?
Positive number that is less than tau.
Yeah, why is this less than tau? Less than tau, like right here and right here. How would you explain that to someone who's coming to you for tutoring?
Magic. Because t squared is greater than 4 delta.
Yes, that is,
No.
yes, no, that's true, that is true. T squared is greater than 4 delta. And then this thing here, so this thing here is a little bit less than tau. No matter how big delta is, you're taking a little bit off of it right
Because
here.
we know that the solutions are real.
Yes, exactly. And because delta's positive on this side, I guess that's what I'm thinking, right? Like delta's a positive number on this side. So you're taking tau squared minus a little bit, so it becomes less than tau in general. So what we have is like two different eigenvalues that are roughly the same. They're the same sign, but they're different magnitudes. So let's say this one's the slow one, this is the small magnitude. And this one is the fast. And that lambda actually corresponds to velocity on that eigendirection. So this is large magnitude, larger mag, right here. The way to sketch these is you're always tangential to the slow direction.
I love that.
So these look like parabolas, and then so you start off tangential to the slow, and you become parallel to the fast. And he actually says this in the book, but it's a nice, like, just way to think about getting a decent sketch out of this thing. You see that? So down here, so here, let's say this is the slow one. This is like lambda equals 1. Let's say this one is lambda equals 2.
So I leave 0 tangential to the slope and become parallel to the fast, and I leave tangential to the slope and become parallel to the fast. So this is an unstable node. There's nothing, so if tau is positive here, if tau is positive, let's also put a little note here. The tau, this should be a plus tau, isn't it? In the way I,
Yes.
yes, thank you, cool. So note that if tau is positive, we have unstable. And if tau is negative, we have stable. So that actually tells us there's like two halves to this plane. There's this unstable half up here and stable half below. So up here, tau is greater than 0, so it's unstable. Just like we saw here with these two eigenvalues in this example. And then tau is less than 0 here, so this is stable region. And so these are called just source nodes. So in here, I have unstable nodes, source nodes. Down here, in this little crescent, I have stable nodes because tau is negative. So these are sink nodes.
I remember these words. I like these words.
You like these words?
I understand these words.
Good. I'm glad that makes you happy, Cindy. That is fantastic. So then in here, hey, let's talk about this real quick. This is like this whole region over here with not a lot of division. What happens when delta is negative out here? What does this do when delta is negative? Can you kind of like get a sense, what kind of eigenvalues am I getting out?
Minus a negative.
Yeah, so delta's a negative number, non-zero, negative number. What does this do? Delta negative. What does that say about tau squared minus 4 delta relative to tau squared? Which of these two is bigger?
Tau squared minus 4 delta.
Yeah, because you're adding a little bit, right? So if delta's negative, this is a little bit bigger. So that means this thing is bigger than tau in magnitude. So square root of tau squared minus 4 delta is greater than the magnitude of tau. Bigger in magnitude. So I'm taking something that's bigger in magnitude and I'm adding and subtracting it. One has to be positive and one has to be negative. Because this, does that make sense? Because this thing here is bigger than tau in value, in magnitude. So this gives us two opposite signed evals. And that means we're gonna have something like this. You've got like a negative corresponding to that eigenvector. You've got a positive. You got a sink on one, a source on the other. And this was like the first one we did together.
Yes.
And I add the consistent flow lines here. And that's a saddle node.
Yes.
So it's not stable in any way, shape, or form. There's like one place that's stable and it's a hair's breadth wide, right? You fall off of that, everything, you're just like, your life's chaos, yes. So out here, in this whole left plane, where delta is negative, if I know that, I have a saddle node.
Okay.
So those live out there. Bless you. Some. What happens when tau is 0? What's happening on the delta axis? The positive delta axis. So look at the thing, now tau is negative, tau is 0. So what kind of eigenvalues will I have when tau is 0?
When delta 0 or when
When tau is 0. When tau is 0 and we're thinking about delta being positive. So let me make that a little clearer. So we have the case where delta is positive, tau is 0. What does this formula do? Or tell us?
SLS.
What's that?
I said SOS.
And so,
So you're gonna have a negative under the radical.
yeah, so negative under the radical.
Very complex.
Complex, right? And so this would be just a pure imaginary number. So
Also, it's not so bad.
it's not,
It's
it is,
not
there's
such
no
an
S.
SOS. Because it's not like exploding.
Not
You're just
even
gonna have a
close.
fun little circle.
Absolutely, it's
Okay,
just
okay,
lovely.
okay, good.
So here we get these kind of things. We get these non-decreasing, non-growing circular orbits, and these are called centers.
And that's inside of that graph?
That's in there. That's on this axis only. So the centers live on this axis.
Does that make sense?
And they're a precarious
But we don't-
thing.
Do we draw them?
Oh, we will draw them eventually, but I would just put a little, they're just like circular orbits.
Okay.
So remember then we also said when tau is positive, things become unstable. When tau is negative, things become stable. If I fall off the center line, what do you think the behavior is in this region? Here we're spiraling, here we become unstable. What do you think is in here?
It's making spiraling and unstable.
Unstable spirals.
Oh,
Does that make sense?
because now you have a positive plus
Yes,
or minus,
yes,
and then underneath it'll be stable.
absolutely. And then down here is stable spirals. And then all along on this edge, on the parabola itself, we've got some kind of weird transition between spirals and non-spiraling things. So this is the transition line right here, and it is a precarious place as well. Not quite, because you don't lose stability. This is really dangerous right here, because your life is going to change drastically. Down here, less. So these are called degenerate nodes, which is just great. I love that. I want to be a degenerate node when I grow up.
I am.
Oh, I am.
Is
Yeah.
that true of the lines?
I'm sorry, say that again.
So the bottom line is called a degenerate node?
Yes, same thing.
Okay.
Yes.
So then
Degen.
at the top, where we have our source nodes, it's just anything in that region is a source node.
Yes.
Got it.
Yes. So we can use this to do quick and dirty, bless you, quick and easy classifications. But what's kind of cool is just to see the lay of the land, how these things relate. And this, I've never seen anyone do this diagram but Strogatz, and I think it's beautiful. It's a beautiful map of the realm of behaviors. So let's do some shit. Let's actually.
I need some more pictures with this.
We need more pictures. We're gonna do a lot of pictures because I can't wait anymore. So we're gonna let R of T. So R and J are two people. Yay, we're finally there.
Cool.
These are two people
Oh.
involved in a relationship somehow. It could be romantic, it doesn't have to be, but they're like invested in each other in some way in their lives. There's some energy going on there. So what we're gonna do is think about their rates of change of love, the velocity of love for each of them. So this is R dot of T equals the rate of change of, actually let's slow down a little bit. Just put R of T, no dots. Let's just, so this equals R's love, hate for J. And J of T, this value that comes out is J's love, hate for R. And what do I mean by that? So a positive value is love.
Okay. Good.
Yes. 0 is indifference,
I mean, you're all right.
Rough.
and negative is, less than love.
Less than love.
So I don't always say hate, but like I'll just put it up here anyway. Hate. Not a lack of fondness. And the greater these magnitudes grow, the greater that emotion grows. So 1,000, R equals 1,000 is head over heels. R equals 1 is pretty okay.
You're mid.
R equals 0 is who? J who?
Weird.
So, does this make sense, this basic setup?
Yeah.
So what we're gonna do is we're gonna set up a system to understand their relationship for different types of relationship models that people have for themselves. So, this should be a C plus D, J there.
A.
So this is the rate of change of R's love for J. This is the rate of change of J's love for R. So now we can have fun. This is where it becomes so freaking fun. So let's set up some models and see if we can just like maybe, the fun part, like one of your problems is come up with some names for these relationship styles. And that's the only thing you have to do is kind of like understand how it would act long-term by using the classifications that we're talking about.
Divorce.
Yeah, well, maybe sometimes, you know. So
Can I call one of them divorce?
So keep in mind that this is just a linear system, like we've been doing. And so everything comes down to these coefficients right here. And from there, we'll be able to figure out what's gonna go on with these folks. So, let's say we have the rate of change of R's love for J depends solely on R's current feelings for J. So, if R is in love with J, it just gets better and better all the time, right? This is a little self-absorbed, but that's okay. If R is hating on J, if R is negative already, then the hate just grows because the growth rate will be negative.
Okay.
Does that make sense?
Yeah.
Yeah. And then J is, well, let's just say J is kind of the same kind of person. They are completely in their own worlds.
Okay.
So if J has good feelings, if this is positive for R, then that just keeps growing. If they're negative feelings, then the growth rate is negative and they just decay. So let's first convert this into a matrix.
Sure.
And remember how this is going to work. So here we have a matrix that's 1, 0, 0, 1. So let's just call that A. That's our A matrix.
Oh, okay.
So good so far? Yeah?
Yeah.
Okay, cool. Tell me what to expect. We have one fixed point, it's at the origin. So our fixed point is the origin. In all these, it pretty much is. In all these linear systems, when it becomes nonlinear, that changes. What is the relationship? Come up with tau, find delta. Look at tau squared minus 4 delta and figure out what's up. Where do you fall in that map? And I'm going to leave you with, I'm going to put this one up too. Because once you get the hang of this, and I mostly because I have to go pee. Just toss that one up too. See if you can just come up with a story about that one. Even if you get this one and then do as much as you want on that one. I'll be right back.
How am I supposed to be finding?
Oh, tell us a trace. Oh.
Matrix amazing.
term?
Determinative.
Oh, so this maybe was a bad one to pick because we didn't quite talk. What do I have going on here? What does my eigenvalue look like? Remember, so it's this.
Tau is equal to a plus d,
Tau is the trace, so it's a plus d, so that's 2.
and
Yep.
then delta the term.
Yeah. What kind of eigenvalues do I have?
Repeating.
Repeating, indeed. Are they positive or negative?
Positive.
They are positive, absolutely. So here we have a repeated positive eval. And there will be 2 eigenvectors associated with that. Finding those is kind of a tricky, it's actually it's a tricky thing that I don't want to worry about. But we will have 2 eigenvectors. Actually, I think
I don't think here,
we'll just have 1 eigenvector, actually. What are you gonna say?
when we go to solve the matrix, it's kind of funny. It's gonna be a 0 matrix.
Ooh, what do you mean by that? I see what you mean. Oh, okay, so let's actually look at that. When we got the eigenvectors, we would take this minus the 1, right? So yes, so we get this. You are right, Kayla.
So then, what does that mean? If
That
we're
means
thinking about-
everything is an eigendirection. So that
Oh,
means,
that makes sense though.
yeah.
Because if everything's based about your personal motion. Okay.
Yeah, exactly. So here, notice that V1 and V2 can be anything. And so we would just pick a couple. We would probably want to get out, I think this is just like everything just coming in on a straight, going out on a straight line. I think so. We'd have to like get a flow chart out and get some actual more details than this. But the key thing I wanted you to see is that it's just unstable and not rotating. That's really all we need to know here, is that the long-term behavior is wherever they find themselves at the moment we ask this question. So if they're here, so here's R, here's J. So if R loves J, but J does not like R, we're right here in this, right? So here, this is love, love. This is love, hate, or hate, love, if we're doing X, Y. This is hate, hate,
Hate, hate.
hate, hate, hate. And then this is
Love, hate.
love, hate, if we're doing R, J. So what happens is those emotions just grow and grow and grow. R grows deeper in love. J grows deeper in despising, disposition.
Disposition.
So it could be okay for them in some ways. If they were feeling, if when we caught them, they were both in love, then they would stay in love forever and grow and then like explode in their crapulence, their mutual love for each other, and drive everyone away because they're just gross.
Win-win situation, I guess.
Yeah. So yeah, exactly. So this situation, there's all sorts of different long-term possibilities depending on the initial possibility. So long-term outcome depends solely on initial state. And that's kind of true here, but we're like thinking in terms of like relationship status, relationship-wise. Nothing changes much except the magnitude of those emotions. How about this one? Did you have any time to think about what kind of relationship this is? What kind of people are R and J, if that's what governs their life, their time together?
Depend on each other.
Yeah. So, like, what does this mean here? So R's love grows for J when J loves R.
Yeah.
Yeah. When J doesn't like R, R's love diminishes.
That's a healthier relationship there.
It seems a little
I'm gonna
healthier.
say that's a little
Yeah.
healthier
I
than
think it's healthier than the previous.
I would.
But
I would
not
agree.
totally healthy, right?
No,
Right.
yeah.
A
it's
lot of
not
codependency
perfect.
here.
A lot of codependency.
Listen.
Yeah, exactly. It's
RJ
like,
to go to
do
therapy.
you have any thoughts of your own?
Truly.
Yeah.
Truly.
Because if R did, then we would toss that in like this. So if R was actually taking their own emotions into
Yes.
account, then we could make this a more complicated scenario. But as it stands right now, what is our matrix? What does my matrix look like for this system? Zero. So what's okay?
0, 1, 0.
Yeah, exactly. Does that make sense? You see how because we're doing this, right? You think of this. So, and this is the R dot row, and this is the J dot row. So R dot is that dotted with that. J dot is that dotted with that. Yeah. So, we find our two quantities. What's tau?
0.
0. What's delta?
1.
-1. Yep, -1. That's all good. That's all good.
The
So on,
negatives today.
it's all good. It's all good. So on this realm, the delta tau realm, where do I live? What is this realm? Saddles. So this is saddles. I have two different signed eigenvalues and two different eigenvectors. So this is a saddle node that governs this relationship. Now we would probably want to get in here and find the exact details, but I'm pretty sure one of them is on the 45 degree and the other's on the other 45 degree line. And one of these is going to be positive and one of these is going to be a negative flow. So if this is R and J, we can, part of what you'll need to do for your homework is actually get these specifics, and hopefully we'll talk about this on Monday when we get back together. I would love that. But there's there's actually a lot of possibilities here, but remember how these work. We have trajectories that are consistent with the eigendirections. So the flows are like this. So it really depends on initial conditions, what happens long term. But they could start out down here where J feels bad about R, but R feels good about J, and have things end up okay. See, like long term, it just starts, and then they end up like getting much better. And there's actually a whole realm, this whole top half in this on this diagonal. Things end up pretty good eventually, right? Rocky at start, but someone woos someone else or convinces them they're all good. However, on this side over here, things are less than ideal.
Top half is where we went to couples therapy. We listened to each other.
Yes.
We heard each other's feelings.
Yes.
And now we're better. And then the bottom half, we didn't go to couples therapy.
We did not. No,
Not
we
participate.
just drank a lot together.
We did. We were
I've been in
toxic.
this one.
We're horrible for each other.
Just got angrier and angrier at each other, and the resentment grew.
Divorce.
Divorce, hopefully,
Sued for the
eventually.
entire house, the
Yes.
kids, everything.
That's right, or cats and dogs, as the case may be. But
Lawn-
yeah,
Lawnmowers, cars, everything.
so this is kind of fun. Yeah.
So, has anyone ever attempted to do this for like is this what dating, matchmakers do?
Yeah.
Wouldn't that be interesting?
It would.
A whole new approach
It would.
to
You would-
matchmaking.
Dating apps are just these
What?
Someone's in the back doing
systems and R's and J's
plain
and stuff.
analysis.
So this is kind of low self-esteemville, though, in some ways, right?
It's not.
Yeah.
Isn't it? I mean, you're not thinking, all you care about is if they love me, then that's all I need.
We have validation issues. So many validation issues.
Yes, yes,
So the previous one was strictly unstable,
yes.
Uh-huh.
but this doesn't necessarily, what would we call
So this is a saddle. I would just call it a
Just a
saddle.
saddle,
Because in some ways it is unstable as well. I mean, you're always moving away. But there's actually stable parts. Like there's this one chance, this very fine chance that the relationship just fizzles out and heads to zero.
But on good terms.
I think that's
It's not divorce or anything. It's
This
just,
one's R hates J, this one J loves R here.
he just gets can't handle it anymore.
You guys can't take it anymore.
can't take it
You're
anymore.
obsessed with me.
Yeah.
I love this
That's
so
it.
much.
And down here too, you could have the one hates the other one. Their amount of hate and love respectively is equal. And so they land on these perfect diagonals and then things just fizzle out. They need a little imbalance to get things cooking.
They need a healthy relationship is what they
They do.
first of all.
So it's not strictly thank you for
Yes, exactly. So let's see, let's take a look at another one. I don't know, help me make one up and let's analyze it.
Can we do R, like J minus R?
Oh, I like it, for who?
For R.
For R, so we'll do J.
Or R minus.
No, I'll
that's
do it
fine.
like you said, I just wanna keep them in the
Yeah.
right order. Okay, so what does this mean here for R? Like, what's the personality type?
So R's love for J.
So the rate of, the change in that love for J depends on,
it's negative toward the self,
yeah, so the more R loves J,
the less
it slows them down, right? They're kind of like, the more they start to love J, they're like, okay, I'm starting to feel I gotta back off.
overcommitted.
Little, yeah, or worried about commitment, maybe.
Yeah.
We have some hesitation here.
Hesitation.
Okay,
Okay.
for
And
sure.
then, also like, the more J loves them, the more they love J.
Okay.
And the more J
Okay,
dislikes
yeah.
them, the more they dislike J. So this
Okay.
is almost like the healthiest thing we've seen so far, I think.
Wow. We've had some pretty unhealthy things,
It's not
Dr. T.
hard to be healthy at this
Yeah,
point.
it is. So what about J? What does J act like? Let's come up with.
What if we did 5R?
Ooh.
Oh, we haven't put numbers in here yet.
Oh, we haven't, no, so,
Plus
yeah, magnitude.
J.
Plus J?
Sure.
Is that what you said? No, it's up to
Yeah,
you.
it's
Is that okay? Yeah.
You can do whatever you want.
Go crazy.
So yeah, let's do it. Let's make it super crazy.
Woo! Okay, so J's love for R is super amplified by, so they like really hinge off of what the other person, they're getting off the other person, right?
Yeah.
Yeah, like, I think they like me, and then they're like buying wedding gear and
Yeah,
stuff. and-
but that
yeah.
would be catastrophic if R is like.
Yes, exactly, yeah,
Oh no.
yeah.
Oh no.
But at least they pick up on signals,
Yes,
right?
that's
So
important.
they're actually picking up on like, I don't think they like me all that much. This is
Communication.
good.
I love this.
And then they kick their own emotions in. So if they're weighing R's reactions more than their own. So this is a little healthier. This is not so healthy, right? It's fine.
Okay.
So what does their relationship do? Tell me.
Oh, Jesus.
Find out. Figure it out.
Jesus.
Crank out a matrix like you should with your own life when you have relationship
Oh, we don't need to do.
This is what we sit
This
down.
one.
Pro and con list. I built a matrix. And I evaluate the likelihood that our
Do you
flow
even
will
want it?
converge
Nerds in
properly.
love.
Do you even want to be in a relationship with me? I don't know. Let me ask my matrix.
What do you-
Let me see where this is going.
What is your trajectory? We're gonna find out together.
We're in a saddle node right now, actually. I'm not really
Is
sure
this,
if
you
it's
thinking
gonna
this is?
work.
This is a completely degenerate node of a relationship.
The most degenerative.
Did you? Uh-huh. I knew what you meant, Kayla. It's okay.
Did I stutter?
She might have, but she meant what she said.
I did stutter. That's okay.
That's phenomenal.
Yeah, I don't know. I don't know what to expect here.
It's gonna be special.
It is. But it is a nice, tau is 0, so that's kind of, it's precarious for sure.
interesting.
So you get the same thing, huh?
Yeah.
Yeah.
It's real negative.
That's real nice.
It's real negative. So it is gonna be a saddle.
It is. It is.
So we might have some good things come out of this.
It seems like, yeah, we should, let's see, let me crank out the exact eigenvalues. So
Yeah.
let's see here, so lambda equals.
Last time you were able to just see it.
Yeah, I don't think I'll be able to on this one. I've seen that one a bunch of times, so I was kind of like, so then this is just 0 squared minus, so plus 24,
Yeah.
2.
Oh.
So square root of 24 is 2 square root of 6.
Sounds about right.
2 plus or minus that, so plus or minus root 6. Not fun to find the eigen.
Not fun.
Let's do the, let's just do, I'll carry through the plus minus.
Absolutely.
So you can kind of do, but you can sometimes do both eigenvalues, vectors at the same time. So, and we're subtracting them off, right? So it's minus
Yeah.
plus,
Excuse me.
1.
There was an intense sound though there.
There was really deep bass.
I didn't like that.
We got this, and let's see here, so then, what could you get? Negative 1 plus or minus root. And the one thing to remember is with the eigenvalue, eigenvector equations, you only need one. You don't have to worry about both of them. Because they'll both tell you the same thing, even though this looks incredibly different than this, it's the same shit. So, it is the same shit. I like this 1 here, I can't really argue with that. So, I would just like let V1 equal 1. And then, because you can pick anything you want, because there's infinitely many solutions. So V2 equals just the opposite of that. So here's our so we've got lambda, so plus or minus 6 corresponds to 1,
Whoa.
1 for the first component, and then 1 minus plus root 6 for the second. Square root of 6 is like 2 something,
Give or take.
give or take. So you've got a negative here, and then a positive here, and a positive of fairly decent magnitude, well, relative. So let's see. So yeah, let's just say square root of 6 is like 2 for our shitty little drawing. And so then I've got 1, 3, something like that. And that corresponds, I'm doing the plus here, and that corresponds to the negative, so that's stable there. That, bad. And then the other one's like 1 minus 1. So like this, not quite as steep, and that's the source direction. So, in some ways, you know, all these saddle things look kind of the same. It doesn't look like they can end up in love at all.
Honestly, no.
Yeah, there's no happy outcome. Like if that isn't necessarily a happy outcome just because two people don't stay together. That's not bad. Sometimes that's great.
I'm so glad we analyzed the love lives of RJ today.
You're gonna get to do it some more.
Not until.
So yeah, that's actually pretty interesting. Yeah.
So like on the other saddle note, the one that we did before it,
Yeah.
there was a possibility that they could end up
Yeah.
in love or whatever.
What do you think? So what's the greatest likelihood of the outcome here? Like long term?
Divorce.
What's somebody
How would you characterize the, like what, okay.
yeah.
Yeah, I think.
Right? Like, because almost every route leads to this quadrant or this quadrant.
Mhm.
So this is where somebody's in a lot of love, somebody's in a lot of
Oh,
hate.
that's so
This is
sad.
pain. There's a lot of pain here.
God, wow.
We might have just come up with an even unhealthier one.
I remember when you were like, this is so good. They have good, healthy. No.
Wrong.
It just goes to show you, it
Incorrect.
doesn't matter.
Sometimes
Sorry,
it's
R.
just,
Sorry, Jay.
it's just the right mixture.
We might find you a happy
This is like one of my favorite math things ever, what we've just done. And we're gonna make it more interesting too. When we make nonlinear, oh man, then it's gonna get crazy. Nonlinear next Monday.
So really, nonlinear is probably best to model a
Yes,
relationship.
100%, 100%. So this is what I was trying to teach those lousy honor students that they hated so much.
How's the honors students?
Why?
Because
If I would, can I just say, if I was in honors class and I pulled up and this is what we were talking about, I'd be like,
I know you were in the one right after I like called it quits. I felt that was the only thing I regretted.
It
Were
was
you in there
so
too?
sad.
Were you two in the same? Are you two in
Yeah.
the same? Oh, you would have been. Oh, sorry.
Oh,
You would have
sorry.
loved. You would have loved that class.
I think knowing the rest of our class though, they probably
They
would
would have
hated it.
we read a physics book and literally there was like
It was
two
like pulling
people
teeth.
that liked it.
What book did you read?
Until the End of Time by Brian Greene.
Yeah,
Ooh.
I loved it.